Hello, welcome to some video notes. We're going to go through the third lesson of the drummer unit. Today we're going to be going through the section called Singer. And so we're going to, and story-wise, we're going to connect this to the singer that's going to join the band. But in order to rate the singers, we're going to be learning about things called frequency and pitch, or basically the highness or the lowness of a note, or the highness or lowness of a sound wave. And then we'll also be learning about wavelength and how frequency and wavelength are connected to each other. So today, gonna kind of recognize the idea of what frequency actually is, and the idea that it's measured in a special unit called hertz, or Hz, there you can see on the screen, to measure the number of vibrations, basically the number of vibrations in a sound wave per second is what hertz actually is measuring, or what a frequency actually is. And then we're looking at the connection between frequency and pitch, right? So the number of vibrations and what that sounds like to us, and then also looking at wavelength as well. So remember Zane Shearing here, the guy that we're following along through our storyline. So we're kind of jumping ahead a little bit from where our last part of the unit was. And so now he's got a full band. He's got a guitarist, he's got his drums, he's got a bassist, right? Everything's kind of working together really, really well. Except the singer that they have, even though she, looks good, she's got the right kind of look for like a leading singer for a band, she can't sing very well, right? She doesn't hit the right pitches. She kind of sounds off key, right? So you guys have probably heard someone who sings badly, right? And doesn't really follow the music or doesn't hit the tone of the music like it's supposed to, right? So obviously it's not going to be so great for their performance on the street if they want to be making money off of their performance. People standing around listening to the singing, right, is going to help to build that crowd, want them to donate to this band so they can make some money. And if the singer's not very good, that's going to lower everyone's chance of surviving and living this type of lifestyle. So they probably need to get a better singer, right? And they want some help from us, remember, we're the agents that are trying to help this band succeed. So in order to do this, right, we're going to get a bunch of singers to kind of go through kind of a recording studio, and we're going to have them sing into different types of equipment or specific piece of equipment in order to try to kind of sort out whether they have the right singing ability. So rather than just listening to the singers and thinking, oh, can they sing very well? Let's do this scientifically. Let's actually collect some data on the frequency that they produce, or they can produce, right? The sounds that they can produce, the pitches that they can produce. And we can measure it using devices similar to what we were talking about with our oscilloscope, right? So we can actually get data on the sound wave itself. So the band has particular specific needs. They need to have a singer who can sing all the way down to a middle C and all the way up to a very top A, right? So it's got quite a long range that they'd be able to hit. And so most people can probably sing, at least people that are fairly good singers, can cover a lot of the notes that are in between those 2 points, but really got to make sure that they can hit the very low note and the very, very high note in order to make sure they fit within the range necessary. So we need to test them for this audition, right? We need to figure out a way to collecting some data on whether or not they can hit these notes, right? The high note, the low note, and all the note in between. And so in order to do this, we're going to get some equipment, right? And we're going to kind of devise a little singing test for them. And we're going to use something like an oscilloscope, or here, something a little bit easier that you guys may be more familiar with. Similar to the idea of an oscilloscope. So this could be what was called a tuner, right? And so if you have an instrument at home, you might have used one of these before to make sure that you are playing in tune, right? And so it's got a little microphone here, just like an oscilloscope has a microphone. And you can set it to say, oh, I want to have a particular note, right? I want to sing a G or a C or an F sharp, right? Or, middle C or high A. It will then set inside, the little computer will set the settings to what that vibration should be, what the frequency or the sound wave should sound like. And then the little bar here will tell you whether or not you are on, if you're in tune, right? So normally they have a little light there as well. The green light tells you that you are in tune, right? You are hitting that frequency. And if you're a little bit higher or a little bit lower, if you're a little bit sharp or a little bit flat, right? You've got the kind of a range that the arrow would be pointing to. And then there will be red lights to tell you if you're flat or if you're sharp, okay? So that's kind of how pitch can be measured, right? We can be looking at the number of the number of vibrations that occur in every second, or which is a specific frequency. So we can think about it in terms of our oscilloscope as well. Remember, we looked at this in the last class. So we saw with amplitude that the size of the waves increases right, as the amplitude goes up, or they get smaller as the amplitude goes down. With frequency, though, it's not the size of the waves, it's the number of waves. And since frequency is the measurement of the number of vibrations or the number of waves we would have in a single second, if we were to increase frequency, we would expect there to be more waves within a 1 second period on our screen. If we were to decrease frequency, there would be less waves in 1 second of a screen. So we're going to use this type of scientific equipment, right, to collect some data on these singers to evaluate them, right? Now, before we can kind of dive into the look and see what these results are, you probably need to have a little better understanding what frequency actually is. And so we're going to have some questions to look at frequency overall in the sound waves and how frequency and sound waves kind of look differently from each other. So you have some questions, right, on your notes. You're going to kind of follow along with the video I'm about to show. And just to be aware that some parts of the video you might think are silent, or maybe your audio on your computer or your laptop is not high enough, but they will be, you can hear them, right, you eventually. So as we have very low sound waves, very, very low frequency, sorry, not low sound waves, but low frequency actually can be very difficult for us to hear, right? And so as the frequency increases, it can be easier to hear it. And so you're going to see part of a video that goes through that. And so it's important that you don't just turn up the volume hoping that you're going to hear it earlier, because listening to a high frequency sound, but also at a very, very high amplitude, isn't very good for your ears, right? Remember, we kind of talked about that a little bit in an earlier class. So just don't mess around with your volume very much. If you can hear me now, right, you're going to hear perfectly fine during the video. At some point you will be able to hear it. Okay, so let's go through it. That's changing amplitude, right? Now we change frequency. There's less waves at lower frequency. Okay, so let's listen to frequency increasing from 20 to 5,000 hertz. So again, don't change your volume. You won't hear it for the first part. You guys see the frequency line is increasing in the number of waves every time we increase the hertz. Again, these low frequencies you might not hear very well. Okay. You start to hear it? Sounds like a distant car engine. More waves as the hertz goes up. If you don't like the sound, you can mute it. If you don't want to hear it. And look how many sound waves a second. Over 3,000 sound waves, vibrations, right? A second. Okay, let me stop there. All right, so you can see, look at that line compared to when we first started. It was like almost flat at 20 hertz, all the way up to 5,000 hertz. So we went from 20 vibrations a second to 5,000 vibrations a second, right? So we had a dramatic increase in the number of these waves that we can see on the screen, right? Okay, so then again, through our oscilloscope, this is what frequency would look like. So here, we turn our oscilloscope on, we have a low frequency. We have a single wave here. This would be a hertz of 1. If this is 1 second of time on our x-axis, right, going from the x-axis, going down, up, and then back to the x-axis again, that's one wave. That's one complete wave, right? Or you could also just count the number of peaks or the number of troughs. That's either another way you could do it. But that's a hertz of 1, right? And so if we increase our frequency, right, we can see that we're going to increase the number of waves. We haven't changed the height of the wave because we're not changing amplitude, right? We're just changing the number of waves in our frame by having the frequency increase. So now we've got about 1.5, right? Now we have about 2 hertz. Here's about 2.5, right? Here's about 3, right? And so as we keep increasing the frequency, right, we keep increasing the number of waves within 1 second, it creates a higher and higher pitch, a higher tone. So low frequencies have very low pitch, and high frequencies have very high pitches, okay? Here you guys see, again, just increasing the frequency even more. So if we're ever wanting to know the frequency, if we can see 1 second within our graph, right, if this is 1 second of time, you count the number of waves. Here we've got 1, 2, 3, 4, almost 5. So we're like about 4.5 in terms of our frequency here. Okay, and we go up again. All right, so what we're going to do is I want you to draw a couple examples of frequency on page 8. The numbers they're going to give you are very, very high. I don't want you to worry about having exactly that same number of waves because I don't think you'd fit it in the graph on your paper, on your notes. But just have a large number or a very low number of waves when we look at these, right? So here we have an oscilloscope showing a high frequency wave, right? So just give kind of an example of something like this. You could have this number of waves. Here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9.5, about 9.5 waves or 9.5 hertz. You can have that many, right? You can maybe have about 7 to 9 waves and draw that into your notes, right? So oscilloscope is basically showing frequency. And so high frequency would look like that, right? And so for example, a number like 880. 880 is a pretty high frequency, right? So 880, that's would have 880 of these peaks on your page, right? So you don't have to draw that. Don't draw 880 waves, right, on your graph, on your notes, but you know, have a good number of them, right? Then 880 is just an example of a high frequency, a high wavelength, high pitch. We're having lots and lots of vibrations in 1 second, 880 vibrations in 1 second, right? A low frequency would look more like this. So again, on page 8, you have some space. You can kind of draw in an example of a low frequency wave. So here we've only got 2 or almost 2 full waves here, right? So then it has a hertz of 2, right? Or an example could also be something like 262, right? 262 is a lower number than 880. So 262 hertz would have only 262 vibrations per 1 second versus something like 880, which have 880 vibrations per 1 second. So again, your example doesn't have to have 262 waves on it. Again, that's just not gonna fill in the space. But you can draw an example like this, which has only like 2 or 3 waves compared to the high frequency example, which has like 9 waves. Okay, so you need a little bit more time. Go ahead and add that in and pause the video. But if not, so then let's move on. Right. So the wavelength is also connected to the concept of frequency, because wavelength is the distance between the peaks or the troughs between each wave, right? And so wavelength is actually the inverse of frequency. If the frequency is going up, the wavelength must be getting smaller and smaller. If the frequency goes down, then the wavelength is getting bigger and bigger, because this is what a wavelength actually looks like. The wavelength, if we were to take a ruler and kind of measure this distance here, it's how far do we go between this peak and this peak, right? And so the wavelength is going to be the same between every single wave, because every single wave at a specific frequency has the exact same wavelength. And so as I increase my frequency, as I fit more and more and more waves, or more and more vibrations here within 1 second, they're gonna have to get closer and closer together in order to fit within 1 second. So that means that the length between the waves, the wavelength, is going to have to get smaller and smaller as they crunch together, right? You could think of this idea of like if I was taking a bunch of students and I'm kind of cramming them together inside of an elevator, right? The more students I need to fit inside the elevator, the closer they're going to have to be to each other. So that means the distance between the students is going to decrease as the number of students is increasing. So as the frequency increases, wavelength will decrease, right? Here's an example of we are looking at wavelength at a lower frequency. So you can add this onto your graphs on page 8, right? So if you drew one that only had 2 or 3 waves over the course of that space, right? The 1 second, the space on the graph is the same. So that means that the waves are spread out in order to fit that space. So that means that the distance between the peaks or the troughs, you can do it either way, would be the same, right? Would be longer, right? So the wavelength is going to get longer for lower frequencies, and it would be much shorter for higher frequencies, right? So when we think about frequency and we think about wavelength, they are opposites of each other, or they are inversely proportional, right? So as frequency goes up, wavelength goes down. As frequency goes down, wavelength goes up, all right? So again, if you need more time, you can pause the video to add these notes about wavelengths to your graphs. And if not, then let's go on to kind of like apply this stuff to our scenario. So let's look at our results of the singing competition, the singing auditions that we had with our group, okay? So if we want to have the singers that are going to be joining the group, they need to be able to hit between these 2 frequencies. They need to be going as low as 262 hertz and as high as 180 hertz. So they need to be able to hit a low pitch, 262, or a high pitch at top A, right, at 880. So when we think about the idea of pitch, pitch is like the sound, is the music term for frequency, right? Pitch and frequency are the same thing. Frequency is the number of vibrations in 1 second. Pitch is the sound of the sound wave. Is it a high sound or is it a low sound, right? This is a specific way that the sound wave sounds, right? How we hear it. So if we have a high pitch, the reason why the pitch is high is because there's more vibrations in 1 second of that sound wave, which means that the frequency of the sound wave is higher. So a high pitch has a high frequency. The opposite would be for a low pitch, right? A low pitch has less vibrations in 1 second. And by having less vibrations, right, we would have a lower frequency, because that's what frequency is. It's the number of vibrations in 1 second. So low frequency also has a low pitch, or sounds like a lower volume to us. And as we saw that in that video that we were just watching, as the frequency increased, it started very, very low sound, right? And you've actually even started too low for you probably to really hear it. And then it increased in, as it increased in frequency, it increased in pitch until it eventually became like a really, really high squeaky kind of alarm sound, right? Okay, so frequency and pitch are directly related to each other. If frequency is high, then the pitch is high. If the frequency is low, the pitch is also low. Okay, so frequency in sound is, again, the number of vibrations per second. So you may make sure you be able to identify and explain what frequency actually is. And remember that when you're dealing with science, remember, we have very rarely do we ever have numbers that don't have units. So if you're talking about the frequency of something, you need to make sure that you're using the correct units. And the units for frequency is hertz, H-E-R-T-Z, or just H-Z for short, okay? All right, so then let's look at these results. So you have on page 9, right? Oh, sorry. I'll add to page 9. Sorry, page 9, you have an opportunity here to, again, kind of make this connection between frequency and pitch and wavelength, right? So we've got closer waves for higher frequencies or longer wavelengths for lower frequencies, right? So there's a little bit of an extra practice, this idea of adding this in just to kind of connect these 3 ideas together: frequency, wavelength, and pitch, putting them all together. Okay, so yeah, you can pause, and want to add this example onto page 9. And then now, finally, let's go and let's look at the audition results, right? So the singers, they're going to come in. We're going to suggest that they're going to have to hit these specific frequencies. So we're going to use the oscilloscope to see whether or not they're matching the exact pitch or the exact frequency of our low note of 262 and our high note of 880, and then, you know, seeing that they can hit all the other notes in between as well, but they need to definitely hit the lower note and also hit the higher notes, right? And so they go on and they do the audition, right? And ultimately they find Kezi here, who's going to be the new singer, right? People like her, she's a good performer, but she also has the ability to hit the notes necessary. So we think about how the other ones did, right? We had a whole bunch of other girls that came in to help sing and kind of auditioned for this. But all of the other girls, something kind of went wrong. And so they want to know what went wrong. The other girls here, they want to know why they didn't make the audition. And so let's not just explain it to them as this idea that you didn't sing very well, right? That's not being very helpful. Let's give them some scientific data. Let's give them some numbers that they can reflect on this to show them their singing abilities. All right, so then here, you have in your notes, here is the data that we have from the experiment, right? Or from the auditions. And so we've got our chart here showing us the range that they need to be able to sing. And so the lowest frequency, 262, that was the middle C. The highest frequency was top A, which was 880. And so then each one of the singers here were assessed on three things. They had what was the lowest frequency, the lowest note they could produce, what was the highest note that they could produce, and then whether or not could they hit the middle C when asked to do it, right? When asked to say, sing a middle C, maybe play it on the piano, and then they have to copy the sound. Could they reproduce that sound, that exact frequency when they sing? So then what you want to do, you have on your page here, on your in your note packet, you have some space to kind of explain what happened to each of the singers, or what was good or bad about each one of the singers, all right? So I want you to pause the video and then take some time to reflect on why, and explain using the numbers, why the other girls didn't pass the audition. Okay, so you did that, did your work. All right, so then these are the things that you probably could have said, right? For Jade, right, she hit her middle C really, really well. She hit the 262, right? However, her highest note wasn't high enough, right? She got as low as 220, 220 being lower than 262, that means she could hit middle C, right? Because she could go even lower than that. But having a high of only 698, she's not getting all the way up to the 880 that is necessary, right? So that's why Jade couldn't be accepted. She just couldn't hit the high notes. We looked at Rita. Rita also was really good at hitting her middle C, right? But the highest notes goes up to a 987, which probably is a bit too high, right? And so she might have some difficulty really hitting those high notes if she's naturally just producing volume much, much higher than is necessary, right? So maybe she could hit the 880, but it might be a little bit more difficult if she thinks a high note really is a 987, right? So much, much higher than necessary. So maybe not the best control with her voice. When we think about Mel here was also able to hit the low frequency and the highest frequency. She fits in that range, but she doesn't have the ability to really match a note very well. If you look at, she was asked to do a 262 at a middle C, but she did a 266, which is pretty close. But again, she would sound a little bit sharp, right? It wouldn't really quite be the right note. So it would just kind of sound off a little bit when she was singing. And then we look at Rachel. Rachel had a middle C frequency was a little bit too low, right? And then also she wasn't hitting the high notes as high as she needed to. So she did it to 220, so she could get, you know, lower, or at least to the 262 if she needed to. But when she asked to sing at 262, she did a 259, it made it sound a little flat, right? She's not exactly hitting the right frequency. And then for her high notes, she wasn't getting high enough even to get to the 880. But then we look at Kezi, right? She hit the notes necessary, right? She was able to get low enough to get to the 262, right? Her high notes hitting 880, that means that she's going to be able to match that pitch when she hits her high note every time. And then when asked to reproduce an exact copy or exact replication with her voice of the 262 or the middle C results, right? She was able to do it. She hit the 262 frequency very well. Okay, so then ultimately that's why Kezi gets accepted. She ends up having our best results here. Okay, so if you need more time, you can kind of pause this video to copy this stuff. But if not, then let's go in and kind of review some of the stuff and then start applying it to the biological concepts as well. Okay, so you have these questions in your revision packet. So why don't you take some time, pause the video and to go through them, right? And then after you finish, you can unpause and we'll go through the answers. All right, so you did it. You paused this. You actually did it. Okay, so now we want to say true or false. And then if it's a false statement, we should try to figure out what we would have to correct to make it true. So the first one says frequency of a sound is the number of vibrations per minute. That, of course, is false because it wouldn't be vibrations per minute. It would be vibrations per second, right? We have to change minute into second. For frequency is measured in hertz. That's true. Very good. The symbol for hertz is HT. That is false. It's not HT. It is HZ, right? For 4, the note of a frequency, 262 hertz, is lower than a note for a frequency of 880 hertz. That is correct. Oh, why is it pointing the wrong way? That is correct, right? 5 as well is also correct. Middle C has a frequency of 262 hertz. So if you play a middle C on a guitar, that means that there are 262 vibrations per second, right? That's the frequency in terms of hertz, and that's what hertz means, is vibrations per second. So that's that's true as well. 6, a note of a frequency of 165 hertz is higher than a note of frequency of 220 hertz. That, of course, is not false. It is lower than 220 because the number is also lower than 220. And then for 7, a low pitch note has a high frequency. That, of course, is not true. That is false. It is a low pitch has a low frequency, or a high pitch has a high frequency, right? Okay, and so then in thinking of matching the lines that best describe what we're listening to, what we would be hearing, right? So we have options of a louder sound with a high pitch, a louder sound with a low pitch, quiet sound with a low pitch, and a quiet sound with a high pitch, right? So matching these up, we can draw some lines. This doesn't have a very high frequency because there's not many waves, but the waves are very large. So that is a loud sound, has a high amplitude, but low frequency, right? Which is what would match with there. This one, right, has a quieter sound with a low frequency or low pitch. There's not many waves, and now the waves are much smaller, so that means the amplitude has been turned down. The third one, we're looking at a loud sound that has a high frequency or high pitch. There's many waves, there's many vibrations within 1 second, and then the waves are quite tall. That means the amplitude is pretty is loud, right? It's up. And then for the last one, of course, quieter with a high pitch. There are many waves happening here within 1 second, so it is a higher frequency or higher pitch, but the waves are actually quite small in size, so that means the amplitude has been turned down. Okay, so hopefully you got these all right as well. And again, you can just pause this if you need a little more time to look through this. But if not, then let's go on and look at how we can apply frequency in order to interact with animals and pest control. Oh, sorry, I forgot. Jumping ahead of myself, there's one more page I forgot about. So then you also have this example in your notes. So you can pause this, just kind of match up where everything should go based on, the logical representation of the notes, the number of frequency, the frequency number, right? The hertz number, and then what it would look like on our oscilloscope. Okay, so you did this. Okay, all right, so your high frequency would be like this, right? For your high notes, which would be your medium frequency would be like this, with a medium kind of description. And then low frequency would have very, very low number of waves, right? If we're thinking this in terms of numbers, right? Low hertz would be like 65, a medium, right, would be like 262, and then the high one would be like 1046. Now I know the images don't actually represent those frequencies very well, because 65, there would be 65 waves here, there would be 262 waves here, there would be 1046 waves here. But again, it's kind of difficult to draw all those waves, right? So the oscilloscope isn't accurate towards the number of waves, but the general idea is the same, right? There's many waves here because it's a high frequency. There's less waves here because it's a low frequency or lower frequency. And there's very few waves here because it's the lowest frequency. Okay, so you've done that. Okay, good. So now let's apply this to some biology. So here we go. I keep mentioning this idea. Let's look at frequency and interactions with other animals, right? And so on page 11, we've got some questions and you've got some information about different types of radar and pest control, not radar, but pest control devices that use frequency, right? So someone has written into this idea that they want to get what is a sonic fox deterrent, right? So something that's going to drive foxes away from their property using sonic sound, right? Sonic energy or sound energy, basically, right? And so that's going to send out a high frequency sound. There are foxes that hate that sound, right? That hate the high pitched sound, and so it drives them away from keeping, anywhere near the property. So then the person's asking about what type of sound could they be using, right? Would this sound affect cats as well, or dogs or other animals that they might have on their property? And they said this idea that also that they can't hear the sounds, right? Right? So are they making their dogs unhappy? Are they going to make their babies unhappy, right? So is this something that's going to affect other animals on their property? Is it going to affect them? Is it going to affect older people or younger people? So adults versus babies. And then could we recommend a sonic fox deterrent that would be best to fit their needs, right? So we're going to take in all this information and kind of help this person out by answering a bunch of questions that you have on page 11. So if you take the time, pause the video, go through the information it's presented to you on page 11, right? And answer those questions. All right, you do it, right? You looked at all the information. Okay, so then here's some information that they provided for us to kind of go through and think about these questions. And so the thing is that all living things have a hearing range, right? So for example, an adult human really only goes from about 20 to 16,000 hertz. So you guys remember when we started that video of the frequency, we started about 20, and it really took to maybe about 100 or so, maybe 120 hertz before you were really able to hear it. Technically, a human being can hear as low as 20 hertz, but most people can't really pick it up unless it's a really, really loud volume, unless the amplitude is very, very high. And then as we increase the sound, right, the frequency, we stopped at 5,000 in that video, but technically we could probably go up to 20,000, and a lot of you would be able to hear it. A good number of you might be able to hear it. If your ears are aging a little bit, or maybe you haven't been taking good care of them, maybe listening to things too loudly on your headphones, maybe you're down, around 16,000, maybe even 14,000 hertz. This doesn't necessarily mean that your ears are very bad. It's just that, your ears are kind of worn down from overuse, maybe listening to too high frequency of sounds or too loud of an amplitude of sound, which we'll get into that when we talk about the next section of the unit called plug-in. But all animals have kind of a different range, kind of based around your DNA, based around your genetics, right? Cats, they don't hear as low of a sound, but they can go very, very high, up to 64,000. Same thing with dogs, they can go up to 45,000. And foxes, we don't have their low value, but we have their high value of 65,000. So if we can go up to about 65,000, we could still annoy a fox and would still, not want to be around that sound because it gets produced. And so then there are two different types of fox deterrents that we get information on. Here, we've got fox away, right, which gives us a frequency of 18,000 to 24,000 hertz. And then we also have the fox frightener, which gives us sound from 45,000 to 65,000 hertz. So one of them has a much lower range than the other one. And so when we think about answering these questions, or when you're answering these questions, you have to take all this information into consideration, right? So then let's look at these questions. So first, how does the fox deterrent work, right? Basically, it makes a high frequency sound that annoys the fox and drives them away, right? Just like when we were listening to that video, we got up to 5,000 hertz. Probably some of you did not enjoy that sound, right? Imagine if we'd gone all the way up to 20,000 hertz. Probably would have been quite an annoying high-pitched sound. So 65,000, right, getting all the way up into the 60,000s, would probably be very, very annoying for something like a fox. So it says, why should a 50,000 hertz fox deterrent not affect dogs? We look at the range, right? The dogs carry a max of 45,000 hertz. So the dogs are not going to be deterred from the sound wave from the fox deterrent because they can't hear it, right? Their ears are not capable of picking up that sound wave, so they just hear nothing coming from the device, right? If we look up, should most fox deterrents affect cats? And we would say yes, right? Because cats and foxes have very similar maximum hearing frequencies, right? Cats can hear up to 64,000, foxes go up to 65,000. So there's only a difference of 1,000 hertz. So a lot of fox deterrents are going to be producing sound waves that would annoy a cat, right? Then, should a fox deterrent affect children or adults? No, because really we are maximized at 20,000 hertz. And for most adults, really they're going to be under 16,000 hertz, right? So if it's set above 20,000 hertz, which a lot of Fox deterrents can go, again, it's not going to bother us because we can't even hear it for our brains to really recognize it. And the last one, which would be the best to do based on this person's the problem fact that they live on a farm, they got cats, they might have babies and dogs and things like that. What's the best of the two Fox deterrents to use and why? They should use the Fox Frightener, right? Because it is the best choice as it can be set as high as 65,000, meaning the Fox can still hear the sound waves, but then the cats are not going to be heard. Actually, let me check something. Yes, sorry, the Fox Frightener. Let me make sure I have the right one. Yes, the Fox Frightener is the one that they want to use because it can go all the way up to 65, which means that the cats wouldn't really be bothered by it because they're not going to hear it, but it could still affect the foxes in the area. Okay, so you can pause this if you need more time to kind of write down these answers and catch up on your notes. But if not, then that is it. That is it for today's class. And so you also have some additional practice and thing you could be doing on amplitude. It's not amplitude, frequency and wavelength as well.